Thank you everyone for joining us today. I'd like to welcome all of you to Quantico Energy's webinar series. This episode of our webinar series is going to be Series 1, Episode 1 of Machine Learning and Geosciences. We have the pleasure of our host walking us through some of the more cutting edge technologies that we're seeing today and applications of artificial intelligence in geosciences, particularly in the geology and geophysics domains. Without further ado, I'd love to hand it over to my colleague, Gareth Taylor.
Hi there, many thanks for joining us today. Naturally, I wish we could be presenting the webinar under significantly better circumstances. Let's just hope the virus runs its course in record time and disappears forever. Our first webinar on the Machine Learning and Geosciences series is titled Optimizing Geoscience Workflows with AI Solutions. So I'll start with a brief company overview and introduce a subset of our machine learning technology, showing some compelling examples along the way. I don't plan to get too deeply into the weeds in this session. Subsequent Quantico webinars are designed to do exactly that. For those of you not familiar with Quantico, we were formed in 2012. So very clearly, we're not a startup. We're based in Houston, Texas, and comprise fewer than 15 full-time staff, along with a few consultants. For the most part, the technical staff are either geoscientists or data scientists, with a few well-credentialed individuals who are equally adept in both fields. That mixture of disciplines ensures that our development team and technical services group are building AI products and delivering results that are physically viable from an earth sciences perspective. So let's open with our technology roadmap that shows our focus in three key areas. Firstly, the deployment of proprietary machine learning technology and training models to synthesize elastic log data from sparse MWD gamma ray and drilling data. That's EDR dynamics data. Secondly, applying machine learning technology to gain a rapid understanding of reservoir geometry and reservoir properties. And then thirdly, the commercialization of this technology as plugins to third-party platforms. From a historical perspective, Quantico was formed in 2012, although it shows 2014 on the slide, with the goal of developing a machine learning algorithm that could match the output of Schlumberger's Throughbit technology that's routinely deployed in horizontal well bores to acquire elastic logs, DT, DTS, and density. This required access to significant amount of training data. So from 2012 to 2014, Quantico built a proprietary database by sourcing well log and drilling dynamics data from operators, drillers, and state bureaus. This development resulted in Quantico's first product, QLog, which requires as input, as I mentioned, only gamma ray and the drilling dynamics data as received by the drilling engineers to protect the same elastic log suite as Throughbit, so DT, DTS, and density. This technology was tested for robustness through numerous proof of concept exercises by Shell, Equinor, and Nabors Drilling prior to them becoming Quantico's principal investors. So at the moment, we are rolling out our TechLog plugin, QLog, within Shell, and we hope to have a general release midway through the year. And we've also partnered with Baker and BJ in recent years. In terms of reservoir evaluation, QRes is the tool that we have developed for working with well data, seismic data, and other data, geophysical data types. And we've undertaken some significant projects for Shell, Exxon, Conoco, Aramco, and Repsol, both onshore and offshore, conventional, unconventional plays. And we've recently enjoyed a partnership with CGG and TGS. And the goal there is to add value to their multi-client offerings. So as you will see, delivering Earth models within weeks rather than months is of great interest to these guys' clients. More recently, we've been focused on developing our AI software stack such that we have tools that are now able to enable oil companies to build and maintain AI models. We're in the process of porting our QRes technology to Petrel, and we've undertaken partnerships with Azure, AWS, and Wipro. So today I plan to discuss the impact on workflow optimization using QLog, QRes, and QEarth as examples. However, for completeness, I'll mention a few words on QFrac and QDrill. QFrac with deals effectively with fracking efficiency, whereby we can establish a uniform completion strategy for frac initiation and propagation. Using the output from Q logs at DT, DTS, and row B, QFrac locates zones of low horizontal, minimum horizontal stress, which enables us to minimize stress differentials across and between stages. This results in complex frac propagation patterns, which effectively eliminates hit wells. Also allows us to reduce number of stages, and therefore costs. QDrill addresses the issues related to drilling efficiency. More specifically, the use of real-time measurements of UCS, that's unconfined compressive strength, versus MSE, mechanical specific energy. When a well is being drilled efficiently, UCS and MSE are effectively proxies for one another. However, when drilling dysfunction occurs, UCS and MSE measurements diverge significantly. UCS is seen as being a more reliable measurement of what it takes to break rock, used by drilling companies to identify and remediate drilling dysfunction and mitigate excessive bit wear. So let's launch into QLog. We've co-authored a number of papers over the years with our clients. They're available on our website or through the SPE. So as I mentioned, QLog's machine learning models are trained to simulate vertical, deviated, and horizontal well logs with the same accuracy as a repeat logging run. The compressional and shear sonic and density logs are generated from the standard suite of drilling dynamics data, the EDR data, and the gamma ray and resistivity logs as input parameters. In the lower right, you'll see an example of the output from QLog. So the tracks there from the left are gamma ray, and then we have the three log tracks are the compressional sonic, the shear sonic, and the density. So in blue, we can see the measurements made with the through-bit conveyancing technology from Schlumberger, and in red, you'll see the predictions or simulations that are made using gamma ray, only gamma ray, and drilling data. And you can see there's generally significantly less than 5% variance over that entire measured depth. I mentioned training, and the training clearly is important. This is neural network technology. So as I mentioned, we source data from most of the basins in the US lower 48, and these have tested or have tested variety of different parameters that you can see here, or properties that you'll see here in terms of age, types of rock types, and other properties. The workflow here is that we'll take the input would be the survey data, the gamma ray and resistivity if it's available, and then the drilling dynamics subset. So perhaps weight on bit, torque, rates of penetration, rates of rotation, plus PVT data if it's available, along with offset wells and other information that's appropriate. So the synthetic log models will be developed for the major US basins using drilling data and well logs from our proprietary database. And if we don't have representative data from an area of interest, we can develop these models with perhaps half a dozen wells for international projects, for instance. So the output, as I mentioned, would be compressional shear velocities and density. From here, we can derive fracture quality, Young's modulus, Poisson's ratio, min-max horizontal stresses, differential horizontal stress ratios, brittleness, etc., and then a suite of classic reservoir quality attributes. So as I mentioned, we have worked or deployed QLog in most of the lower 48 unconventional plays, and here's an example of 6 of them. All of these are depicting generally our compressional sonic along the top, our sheared sonic in the middle, and then our measured density as the lower track there as a function of measured property and depth. So you can see one of the advantages here, if we zoom in on this density here, is that the measured density is an extremely noisy measurement, and you can see that this is not just smoothing through here. This is that there actually is a fair bit of variability in the prediction made by QLog. So this is an example where we deployed QLog in the Gulf of Mexico for Shell. It's a published example in Mississippi Canyon. And the goal here was to determine whether QLog could generate a suite of synthetic sonic logs in the overburden that could be used for higher end geophysical QI purposes. So many of the wells in the Gulf of Mexico aren't logged in the overburden for the elastic properties for many different reasons. And so in this particular case, Shell did log the overburden interval, but then provided us with the gamma ray resistivity and the drilling data, the EDR data. So in this X equals Y plot here, we can see the measured compressional sonic on the vertical axis and the QLog simulated sonic on the horizontal, and you can see there's a nice match up and down that X equals Y line there, and there's no sort of linear alignment showing some sort of systematic error. If we look at if we integrate those data over two-way travel time, so over 18,000 foot here, you can see that the variation here is fairly minimal, so 19 milliseconds over 18,000 feet. And if you generate synthetics from here, you can see that it's also almost a virtual laydown between these two log products, and that manifests itself as a bulk shift. So as the client GIF has said, this was well within the acceptable range of error expected of a repeat run of a conventional logging tool. So the benefits for QLog are that it's extremely fast and efficient. It has the same accuracy as repeat logging. It's significantly cheaper than logging costs, whether deployed in vertical wells or horizontal wells. We recently completed the first real-time operation in the Gulf of Mexico well in deepwater Gulf of Mexico. There are no staff on the site, no tools in the hole, and no radioactive or acoustic sources used. So clearly there are major HSE benefits from this type of approach. A natural adjunct or spin-off, if you will, from QLog would be QInfill. And the idea here is to high-grade well databases specifically for the elastic log. So again, we're going to be using machine learning technology to replace poor quality or missing log data based on EDR and adjacent wells, EDR data and adjacent wells. So clearly you can identify poor data areas with petrophysics or rock physics, where you have missing data here. Clearly you'd like to insert reasonable measurements in those areas. So if there are adjacent wells, offset wells that are more robustly logged through those erroneous areas, then we can train a model to then go ahead and predict the elastic suite of logs that we require, for instance, for generating calibration points for quantitative interpretation purposes, as you see depicted on the right here. So the benefits here would be that we replace erroneous data with physics-constrained data. We replace missing data when tool failures occur, for example. And then it's a tremendous value add potential by high-grading legacy well databases where wells had minimum log suites acquired. So mid to late 90s, there were very few shear wave logs acquired, and so the logs were only really useful in those days for mapping tops into the seismic, so no higher end QI work was possible. And the QLog well curves then are, as I just shown, used to generate synthetics for seismic calibration and QI projects. Let's move on to QRes, which is our Earth model building technology driven by our proprietary machine learning code. So it uses our proprietary machine learning technology to generate high-resolution structural and stratigraphic models populated with reservoir properties. The input to QRes would be very similar to what you would input into a standard model-driven deterministic seismic inversion. So well log data, which could be measured or from QLog, interpreted surfaces, and 2D, 3D seismic pre-stack, post-stack in time, or importantly in depth. So clearly being able to run or develop an Earth model exclusively in the depth domain is of interest, since each time you map or transpose data between time and depth, you run the risk of enhancing the noise. So we also are able to input additional data types for soft constraints, such as maps, isochrons, isocores, facies maps, and geobodies. And also there's a multi-physics capability, because if you have EM data, control source EM data, for instance, gravity magnetic data, as long as the survey or geometries are consistent, we can use those data to constrain our Earth model predictions too. So the output property models or property volumes are in 32-bit seg-y, and then the properties can be anything, any measurement, any property that is logged or measured in the wellbore. So a standard suite of elastic, petroelastic, petrophysical, and geomechanical properties are available, and we would directly invert for those properties. But perhaps more interestingly, because this is a neural network approach, we're able to train the neural network to predict anything that's measured in that wellbore, so such as the EDR data. So something that's of interest and demonstrating relevancy to our drilling engineering colleagues would be to provide volumetric predictions of mud weight, wellbore stability, fracture gradient, MSE, UCS, and friction angle. So the three key themes in terms of the development of QRes were accuracy, resolution, and time to solution. So here's a snapshot of an example where this data set was provided by GPI, Geophysical Pursuits. It's the Flying Dutchman 3D from Upton and Midland counties in West Texas. So we took a subset of that data that had 7 wells, 50 square miles, and 5 surfaces. And on the left-hand side, we see that there's a conventional acoustic impedance inversion that was produced using a very popular, commercially available deterministic inversion scheme. And you can see here we're able to derive about 40 to 60 foot resolution, and this took 3 months to turn around. So the reason it took that time was because the wells had to be worked up for a rock physics perspective. There was some data conditioning, and then there were the issues with deterministic inversion, such as wavelet extraction and low frequency model building, and that's a highly iterative process. On the right hand side, you see the QRes Earth model derived equivalent for acoustic impedance, and here we have 10 to 20 foot resolution. So you can see it's a, given that this is a blind well, this is a remarkably good result. And this took 3 weeks to turn around. So, effectively, 75% of that 3 weeks turnaround was training the neural network. So it's a very, very, very fast process. If we explore this in a bit more detail, in this case, we had 7 wells in the project areas I mentioned, and we were going to deliver an Earth model populated with various reservoir properties of interest from the Upper Wolfcamp down to the Strawn, and we used 6 wells in the training, and then we're going to use those to predict this blind well, which is about 2 miles away from the nearest control well. So here's an example of the processed 3D seismic, which is very nicely processed, and then superimposed on here is our acoustic impedance. From 25,000 to 60,000. So you can see that a nice high resolution result was achieved here. If we look at how this maps through each well, here's an arbitrary line constructed through all 7 wells in this area. And if we look at these individually, here are the predictions at the training well. So you'd expect these to perform reasonably well, although oftentimes in a deterministic world with a model-driven seismic inversion, oftentimes these wells don't tie explicitly because of the problems with estimating an average wavelet. But by and large, these are very nice ties. If we look at the prediction of acoustic impedance at the blind well test, at the blind well, the Upton XV number 1, you can see it's a very nice prediction. There are a few areas where we have some variance in what was measured and what was predicted, but overall, one might imagine that with a little bit of shifting to accommodate any issues in the original imaging, that this would be a very satisfactory tie for a well that was drilled 2 miles away from the nearest control well. So the benefits of QRes are it's 80% faster in our experience than conventional statistical methods. So 3 to 4 weeks total processing time on average. Significantly higher resolution than traditional seismic inversion methods. Typically, we're seeing 10 to 20 foot resolution in areas where we have good seismic and well data. Unique, robust, and repeatable solutions without human bias. So logs and services are variables, not constraints. Highly flexible inputs. So we use maps, production data, basin analysis, and then the outputs would be things like weight on bit, wellbore stability, UCS, in addition to the standard conventional deliverables. So it can be performed on any physics-based attribute, executes in the time or the depth domain, can be used as an input for geocellular static Earth modeling. And its values aligned with our client through a suite of actionable deliverables that we can provide to our clients. Let's finish up with an overview of QEarth. It's an exciting new development for us. Effectively, it represents the nexus of the 2 products we've been talking about here, QLog and QRes, by utilizing a combination of seismic, well logs, and drilling data to generate autonomous Earth models in real time of virtually any property that can be logged or measured in the wellbore. So the machine learning model is dynamically retrained and updated in real time as new log data is being acquired in the wellbore, and that Earth model is then rerun using the updated model. So I'll show you a movie of a simulation of what we're presenting as QEarth. To set the scene here, let me pause this movie and let me just set this to repeat. So what we're looking at here is a QRes derived acoustic impedance volume from the data set that we saw earlier. So this is the entire volume here. So we frame to frame the video, the 3D seismic volume is 14 by 7 miles or 100 square miles, or 259 square kilometers. And the vertical span that you're seeing is 3,000 feet or just over 900 meters. From the wellbore location on the right-hand side to the edge of the seismic on the left is about 1 mile, 1,500 meters. So we've used, in this case, 12 offset wells to train QRes to map acoustic impedance across the entire volume. And we've withheld 1 well, and that's the well that you see drilling up here on the right, up at the top. And you'll see down here that we're annotating each display in depth and time. And these are hours and minutes. So if we set this thing off, you'll see as the well penetrates through the overlying Sprayberry, you'll notice that the data is not updating terribly much. It's because the geology up here is fairly benign and the rock properties are fairly well behaved. But as we get down to where this hand symbol is, you'll see there's quite a dramatic kick because these wells are located quite away from this well location. So we segmented the well log into 50-foot intervals, and we're presenting it to the neural network as a simulated LWD feed. So for the avoidance of doubt, this is a computer simulation of a real-time WITSML feed. As new well log data is received, the neural network is trained on the fly. It takes about 25 minutes to retrain the entire 100 square miles volume and 5 minutes to produce an updated inline and crossline that you're looking at here. As I mentioned, the shallower Clear Fork and Sprayberry formations, we already have a fairly stable prediction of acoustic impedance up there, but the data is dramatically updated as we get into the more complex Wolfkamp sequence. So as you can imagine, this is a tremendous breakthrough in terms of being able to see ahead of the drill bit, and has enormous implications for risk mitigation. So the benefits of QEarth are that we have near real-time access to the reservoir properties I mentioned previously and listed here. Near real-time predictions are made significantly ahead of the bit and laterally away from the bit. So this near real-time awareness of potential drilling hazards could give you a heads up in terms of the presence of shallow water flow, shallow gas, anomalously pressured pockets, top and base of salt, heterogeneity within the salt, such as sand lenses, etc., and subsalt pore pressure. Other considerations would be borehole instability, stuck pipe, lost circulation, hole deviation, and mitigating bit wear. And near real-time update of structure and stratigraphy will aid in the placement of laterals and clearly assist with geosteering. So thank you for your time devoted here for us. If you have any questions, please feel free to email me at gtaylor@quanticoenergy.com or at our general email address of info@quanticoenergy.com. Thank you and goodbye.